Okay, welcome to the guide sheet number 3. Deals with electrical resistance. We have three major factors that affect how uh, electric current moves within a circuit, and that's the potential difference, which provides the energy or uses up the energy in the circuit. There is the current, the flow of the actual charge carriers, and then there is the resistance. The resistance is simply the element. Whatever factors tend to make it more difficult for the charge to get through. If you think about our basic model of current that we talked about during guide sheet 2, we said that electrons would try to move along. Since they are negative charge, they'll move against the electric field direction. But as they do so, they're going to run into blocking atoms that don't want to, that are stuck in place and don't want to let them go by. So in number 1, the base cause of resistance is the same cause that makes the drift velocity of an electron in a wire pretty slow, down about a meter per hour. And that is that the mobile carriers, the electrons, will collide with atoms that are in the resistor and embedded in the material of the resistor and don't want to move or allow them to move by. Okay, so it's nothing to worry about inertia. While electrons do have mass, it's so small it would not be a problem. Electric fields in this kind of a setup do not diminish with distance. If it was a single point charge, they would diminish with different distance, but not when it's a positive and negative charge from a battery or a power supply. And another one to majorly point out is charge is never consumed. Charge is a conserved property of matter. It can't appear or disappear. That'll be important to us throughout our looks at circuits. Okay, number 2, resistance is quantifiable. It can be measured and calculated. Our standard unit is named after the guy who figured out how this all worked, George Simon Ohm, back in the 1800s. And it is called the ohm in his honor. That's his name. Now, a capital O would look an awful lot like a 0, so the decision was made to make the Greek letter omega be the symbol for resistance. So it looks kind of like an upside down horseshoe. It's a capital omega instead of using an O. Okay, so in terms of factors that affect the how much resistance you would have. Now this is a piece of wire, just supposed to be a small piece of wire. This is the side you couldn't see. It's a typical wires are made round on one end. That means this side over here has a cross-sectional area. It's that whole circle. And then the length L of the whole piece of material is simply how long it is. It works similar to water flowing through a pipe. If you try to move water, if you want a lot of water, you can't use a small straw to move a lot of water because it just doesn't have enough space to allow the water to go through. Same thing with wires. If the cross-sectional area is very small, then the resistance goes way up. So if you think about the overhead wires, which carry a lot of current that you might pass under the big towers, those wires are very large. They're big in terms of being around the cross-sectional area. A second factor that affects the resistance is any path that is long is going to have more of those blocking atoms in the way. So the longer the material gets, the longer the wire gets, the more resistance it has. Now another factor that affects it is just the material itself. We talked about insulators and resistors. An insulator would be a material that had such a high resistance that we could say it probably would stop almost all, if not all, the current for most situations. Even metals have different amounts of ability to conduct. So as an example, copper is a good conductor, but gold is an even better conductor. Now, of course, gold's more expensive, but in high-end applications where it's really important that the current work or go through, gold is sometimes used. Platinum is also an excellent conductor. So in some airbag systems, they'll use platinum because they want to make sure it doesn't corrode, and it also does a really good job of conducting the electricity. Okay, so electrical flow will be greatest in a wire which is thin compared to a wire which is thick. So greater in the thinner wire. It's like a straw versus a fire hose. Harder to get the water through the straw. Wire which is long, wire which is short. Again, the long trip is going to be harder, more blocking atoms in your way. Just as the electron needs more energy to get to the end of a longer wire to start with. Copper, plastic. Okay, so plastic's an insulator, so it's going to have a really hard time getting through the plastic. Copper versus silver. So we want the greater resistance. Silver, again, this is a more expensive metal, but it's an excellent conductor. So in a lot of high-end applications, again, they will use silver solder as part of the process to make sure they have really good conductivity. Number 4, the rate at which charge flows through a circuit is. Now, if you think about the process, if you're trying to get the electrons to flow through, and there are more blocking electrons in the way, then that means higher resistance, and that means it's going to be harder to get through, and that means fewer electrons are going to make it through. So it turns out they are inversely related. The higher the resistance, the more difficult it is to get charge through, the less charge will flow through that space. Okay, so for the following pairs of circuit descriptions, choose a circuit that has the greatest current. The current will be greatest in a circuit which has a low resistance. They're inversely related. So we want the greatest current. To get high current, we want low resistance. Again, wires are short, means it's easier for the electrons to get through, so we'll get more of them through, higher current. Wider is better in terms of trying to get more current through. More space just means easier to get past those blocking atoms. Okay, so 12 gauge wire is 1/12 of an inch wide, and 14 gauge wire is 1/14 of an inch wide. Now 1/14 is smaller than 1/12. So 12 gauge wire is actually thicker in terms of its cross-sectional area and actually carries more current. So in gauge, the lower the number, the more current it can actually carry. And again, copper wiring versus silver wiring, we'll get more current flowing through the silver wiring just because it has better conductivity, it has less resistance. Now, it's difficult to make wires out of silver just because that's a very expensive proposition. Okay, so this section that we've just finished through number 5 here covers the basics of the nature of resistance from materials, specifically wires, and that's what we're going to use to move our electrons around to help keep them, give them a place to move through. We'll look next at the relationship between the big three and how they interact.